Today we have our second lecture on operating system security, and today we're more moving into the cloud, where you're still using an operating system, but it might not be in a computer controlled by you anymore. And you might be running across many different systems, and you might have many other people using the same system as you. So today we're dealing with the complexity of how you can do that while still being secure, and how you might get the guarantees that you need from that. So last time was mostly about access control, and this time is mostly about isolation, trying to keep you safe when you've got multi-tenant environments where someone else might be able to rent the same resources from the same cloud provider as you. So what are the challenges in that? Well, how do you stop others, potentially using all the same systems as you, from being able to read your data / hack your software? And I mean really stop them. It's all well and good talking about the isolation that we've talked about in operating systems such as Android, but what about all of the bugs around the edges, all of the edge cases, things like the side channels we talked about in hardware security, or bugs in the code that you're relying to give a certain property, but when you've got millions of lines of code, you really can't guarantee it, right? And how do you even know, if you ask a cloud provider to run some software for you, that they're running the software that you asked for in the exact configuration that you asked for? How do you know that they've not removed some of your security or given you a slightly different set of properties to reduce security? Or how do you know that they're not snooping on you and reporting it to the government? And that's the property of remote attestation, which tells you and proves to you, often using public key methods, what is really going on, even in hardware that you don't have any control over. I.e. again, it's trusted computing. Now, one of the benefits to the cloud when we're talking about security is something that we mentioned previously in networking, which is that networking security and defending a network is really hard. So what you probably want to do is pay someone to do it to amortize the costs rather than having every single company worry about network cybersecurity. And that's one of the things that you get when you're buying into a cloud service. You get that top of the range security administration that's shared between all of the users of that cloud service. And often you get very specific systems as well as controls to each cloud provider. For example, Amazon Web Services identity and access management. That gives you this fine-grained control and the sorts of network security that's been vetted by serious people. But it's also a form of lock-in. If you start using Amazon Web Services security mechanisms, they won't translate over to Google's or Microsoft's clouds, and so you get stuck paying for Amazon services, which is a different perspective on security, but still an important one. You might get access to middleware like the Google App Engine, which will do things like provide only indirect access to networking / the file system, using safe versions of standard APIs that integrate mandatory access control and call other cloud infrastructure, so its usability and security all pre-vetted. And as in many other circumstances, the idea is that when you want to run applications in the cloud, you go via a defense in depth strategy. In your cloud application, you integrate sanitization, mitigation / hardening against bugs, functionality reduction so that your microservice in the cloud only does a very small thing and bans absolutely anything else. Indirection. In the Google App Engine, they run their Python code inside a NACL or SALT sandbox to reduce the amount of bugs that can occur in there in terms of privilege escalation and memory safety, as well as tracing and logging via ptrace to capture and alert on any unexpected syscalls that appear out of this NACL sandbox. As an example of where this creates some perhaps unusual outcomes, there's an article here about Amazon ECS Anywhere, where you pay Amazon to use their software stack on your own local devices rather than in the cloud. And this seems like a really strange thing to do, right? If you're paying Amazon and not using their systems, then what are you paying for? And the answer is you're paying for their elaborate security defense mechanisms and all of the infrastructure around that. It's far easier to get them to provide it than to worry about this yourself in many circumstances, even despite the lock-in issues. Now, isolation appears at many different levels in the operating system software stack, and it depends on the threat model as to how much isolation you'll need. Between processors in an individual operating system, you will get some isolation. See the Android slides from last time on how you can achieve fairly precise file system isolation in ways that you can't achieve, say, on Windows, for example. But it's also typical for operating systems to support isolation within virtual memory. So every single process running on an operating system will have its own view of virtual memory. And each 4K of memory within your processor's virtual address space will be mapped from a virtual page to a physical frame, each 4 kilobytes inside. That's done using a TLB or translation look-aside buffer and then a page table walker in hardware to translate between these. And the structure in that page table looks a little bit like this. What you get is a 64-bit word that translates each 4K virtual page to a 4K physical frame. And you have several different permissions bits that can be set for each page within each process. So you don't only have isolation between the processors, which see different page tables and so can't access each other's pages unless they've been given specific permission by mapping the same frame within both address spaces. What you get is that you get the number to map the virtual page to the frame, that goes in the middle of this, but you also have a flag to check whether it's user mode accessible, this one here. So if you intend to only have the data accessible in kernel mode, that's what is set, and the idea is that user mode can't access it. Now, a speculative execution on that property and an attack on that is meltdown, which is why these days you actually use kernel page table isolation, but we won't worry about that for now. You've got this writable flag, which sets whether a permission should be allowed to write that particular frame, again at this 4K granularity. Over here you have the no execute bit, which is used to make that 4K page and everything inside it not executable. And so if the processor tries to fetch that data as instructions, it will fail. And you'll remember from previous lectures that in most modern operating systems, the rule is that you can't have this one and this one set at the same time, so that you can't execute code that an attacker has written into a buffer, and so they're forced to do return-oriented programming gadgets instead. Now, this one here, the protection keys, is a relatively new feature. What this is designed to do is to set up 16 different regions in every address space that have different permissions set on them. So you store those permissions inside a register, and whenever you want to change the permission of any of those 16 regions, you change just that register. Then, if you load in a page, and that page has this p keys value set to one of 16 different values, you look up that value in the register, and if the permissions don't allow you to do the operation you want, it fails. And what this is useful for is to allow hardware sandboxing inside address spaces, so that even with memory bugs, you can still protect different regions at different times just by setting this one value in a register, instead of walking through the entire page table and manually setting all the bits of every one of those pages. Now, as a bit of performance trivia for you here on how this virtual page to physical frame translation works, what you do is for each process, you have basically a tree data structure. Your virtual address is 48 bits long, and the last 12 bits are used to index into the 4K frame, and so then you've got 36 bits to translate between them. And what you do is you split that 36 up into 4 different groups. The first 9, you look up one of 512 different elements in the page global directory. Each element looks like the element that we saw on the previous slide. That points into the page upper directory, of which you use the next 9 bits, which then chooses the relevant page middle directory, 9 bits again, chooses the relevant page table entry, 9 bits again, and hey presto, in 4 accesses, you've got your virtual to physical translation, which seems like a lot. If you're doing 4 memory accesses per real memory access in the program, then it's a nice security feature. It isolates your different processes, and it means that you get programmability benefits too. But that's really expensive, right? Well, a lot of this is cacheable, so it's really not that bad. There's this table look-aside buffer there, so you don't pay that much of a cost for this security benefit. But the main reason we're mentioning this is because it gets a lot worse in virtualization, which we'll look at in a minute how this expands out when you've got a virtualized operating system running on top of another operating system, as distinct from virtualization as in virtual memory, which you use to allow different processors within a single operating system to operate with their own virtual address spaces. Right, so the protection features you get from page tables, we've discussed some of these already, especially data execution prevention, where you can either have an execute allowed on a page or writable and not both at the same time, because the idea is that the attacker, even though they might be able to control your data buffers and write bad things in there and try to do a buffer overflow and then try and execute their own code, they won't be able to have that buffer be both writable and executable, and so they will be forced to do a return-oriented programming attack instead, where they use code gadgets inside the existing address space that were already there before the attacker got there. The other big one is address space layout randomization, where this hurts your ability to perform return-oriented programming attacks. It doesn't make them impossible because you can de-randomize and work out where things are. But the idea is that you shouldn't know where different data structures in memory are stored. Things should be randomized away. So rather than knowing where all of your, say, return to libc, which is what you use in return-oriented programming, gadgets are in memory, you just don't know, so you can't store them somewhere to use them as a gadget. The big problem with this randomization is that it often isn't that random, especially in a 32-bit operating system. The virtual address space just isn't big enough to randomize that much away, so you don't have very much randomness, you can guess. The other issue is that via various side channels, you can often work out where things are related, and often things are relative to each other anyway. There's not that much randomness you can put in without breaking known layouts that are defined by the language. That's just one form of isolation, and what you'll want to do fundamentally is limit the amount of software resources that things share. And so you've got things called containers, which are the fashionable new thing in town, which is Docker, where you're running inside a single operating system, so it's just a inter-process isolation. But you'll have, above the virtual memory protections that we talked about just, you'll also have forms of filtering and software isolation to limit the amount of code that you share and to limit the things that you do inside the operating system and trap you inside a sort of jail. And then, if you want to be more serious about this, you go to virtualization, e.g. VirtualBox, where you have a whole separate guest operating system on top of a shared host operating system. The other thing that you might call isolation is sandboxing, which you'll have in things like Chrome or the extended Berkeley packet filter, which we'll talk about later, where you've got isolation within the process. What you try and do there is you try and trap something like a piece of JavaScript to a certain region of the address space and don't allow it to read or write outside of that region. So you don't allow it to modify anything outside of there or see any secrets. So the first thing we'll talk about is sandboxing, which basically was pioneered by Sun with the Java virtual machine, where what you do is you restrict the environment in various ways, i.e. you only allow temporary access to a single directory. You don't allow anything inside your sandbox to see the entire file system, so the virtual machine limits the code that it JIT compiles inside it, and you also only provide communication via the same origin policy, where the basic idea is that if it came from the same individual, it's allowed to see it, otherwise it isn't. Often that's interpreted as being the same company. If you're in a browser, that means the same website typically. So everything inside a single website is considered to be same origin, everything that's not is not. Even the adverts running inside the website are allowed to see all of your secrets of that website in a shared origin policy, but we won't worry about that. What you do then is you prevent access of address space outside of a predefined region, i.e. the JavaScript interpreter's memory in a browser. The reason that I've written Spectre Klaxon here is because that's what's meant to happen with the sandbox, and the issue is that even though you might have checks that say bounds check every single access inside your JavaScript, what we've learned from the Spectre attacks is that you can still escape out of it in speculative execution mode and leak all of the secrets outside there. So this kind of isolation is certainly damaged these days from at least a read point of view, if not a write point of view. And there was more about how Spectre works in the second hardware security lecture. Point is, don't believe every guarantee that you read about. You really need to understand the threat models behind them as to whether it will work for your use case. So in Chrome, you get quite a lot of sandboxing because you've got all of these websites that run that certainly don't trust each other. You don't want some random games website to be able to steal your banking details or look at your bank account, right? What you used to do is trap your renderer in its own process because you knew that it was a big code base with lots of potential bugs that was executing arbitrary code from websites, so you jailed it away. But these days you do full site isolation where every site, or at least every site with a different origin, i.e. from a different company, gets its own process, which is again quite expensive, but it's necessary to give even any sort of guarantee against Spectre. If you leave different websites in the same process, even with sandboxing, you still aren't going to get away with not getting Spectred. So you should at least split them up into different processes. Though that's not the only reason you want this process level isolation. It's also there because you accept that with a large code base like that, it's going to have lots of bugs. So you isolate things away to mitigate the impact. Now, this idea of a same origin policy gets really quite complicated when you've got untrusted ads in the same tab from a company. They're all the same origin, right? But nevertheless, you don't want some terrible ad from some unscrupulous vendor of ads who doesn't check their ads properly because, hey, that's hard, to be able to steal all of your password and credit card details, right? And yet there's very little protection against that, even with site isolation. So what are you going to do? And vulnerabilities in Chrome, again, big blob of C++ code full of bugs. It has to be when it's that big. Often get exploited by drive-by download attacks where the browser, either not up to date or it's a 0-day, will be tricked into downloading and executing something even without the user doing anything wrong. The extended Berkeley packet filter is another example of a sandbox, and here, rather than JavaScript or WebAssembly in a browser, this is sandbox user code inside the kernel. BPF, which is what this is based on, is typically for packet filtering and security analysis, and eBPF allows you to do tons more. It allows you to inject arbitrary code at arbitrary points in the kernel, while still supposedly giving guarantees that this is safe. So it allows you a lot of customization in a supposedly safe way. and it's Turing incomplete, so it's guaranteed to terminate and not hang your kernel. And there's no unreachable code allowed, so there are various restrictions to try and make this more secure. You can prevent things like a pointer arithmetic optionally, and you get guaranteed bounds checking in the language too. Modulo, again, Spectre, which is the big attack on anything where you're running inside the same virtual address space, and you can still get out as a result. And that's a big problem that isn't entirely solved. You will also have kernel API filtering based on the type of analysis that you're running. So a network packet filter won't be allowed to run syscalls that aren't network related to try and reduce the attack vector. Now that's sandboxing, where it's inside a process, inside an operating system, and you've got multiple things inside even a single process, and perhaps some API limitations around that too. Virtualization replaces the entire operating system, so it's multiple operating systems running on top of a single host via what we call a hypervisor. And this is really kind of the poster child of what got cloud computing going. The idea is that you can rent what looks like to you as being an entire server in the cloud. It's not really, it's shared with someone else, but it looks like you've got your own entire operating system running. And there's various bits of hardware support that have helped over the years to make this faster, like Intel VTX, which gives new instructions for entering a special virtualization mode, which makes the guest OS think it's running with full privilege, even though it isn't. And so you get some special instructions for that, and it makes things cleaner and faster than what you had by doing it all in software. And why is this more secure than just a process level isolation within an operating system? Well, even though the operating system can provide isolation properties, and even though something like Android probably does quite a good job of it, the hypervisor can be a lot smaller than a full operating system, where millions of lines of C++, we know something will go wrong. And so it's easier to code review and secure, right? Well, that's certainly the hope. It's not clear whether that's true or not. It's difficult to test, but the hope is that it's a lot more secure as a result of being smaller. Again, there's this idea of a reference monitor, where a small thing is easier to secure, and you hope that everything outside of that doesn't need to be trusted. As to why you'd use virtualization, and for when virtualization isn't enough, you'll still, even with having this hypervisor there, you might still get to zero-day vulnerabilities in that virtualization layer, or even there might still be subtle cross-VM information leaks. For example, you are still using the same hardware, so there's still going to be side channels. And if you'd be vulnerable to that sort of attack, then virtualization wouldn't be enough, even though it's more powerful than sandboxing or containers. And so what you do then is you'd pay extra for compartmentalization based on physical hardware, i.e. in the Google Cloud Platform, you can get to sole tenant nodes for extra money. So for one reason that you wouldn't want to necessarily use virtualization unless you had to, is that it is expensive, or at least it can be. So the 4-layer page table walk that I talked about before actually becomes a 24-layer walk in a two-dimensional virtualized system. What you have are the hosts page tables and the guest page tables that form this two-dimensional grid. I mean, you have to do 24 memory accesses in the worst case. And that's an optimization. That's called rapid virtualization indexing, aka nested page tables, aka extended page tables. This is a feature. In the old days, when you didn't have special hardware to do this, and you had to do it all in software in a one-dimensional 4-table lookup, things got really expensive whenever your host changed any of its mappings, and you then had to go into every guest process in the virtualized operating system and change all of its mappings as well. So that was nightmarish. And even this is, again, it's a performance thing, but that matters. It means that the security of virtualization comes at a cost, which is one of the reasons that people are very tempted to move to cheaper but weaker container isolation instead, which we'll talk about in a minute. Now, some of the things that virtualization gives you are that you can have different guests and hosts. You can run a Windows guest on top of an OS X host, for example, or both one Windows and one Linux on top of OS X. The possibilities are endless. You also get flexibility and containment as a result. So you can contain everything inside that OS. You can give your cloud customers pseudo access to their virtualized environment while still isolating them from other tenants, which really is necessary in something like Linux. Most Linux derivatives require quite a lot of ambient privilege to get anything done. It's a real pain to work on a Linux machine without pseudo access. You need it to install anything. Granted, Android is better than that because its setup is more suited to user mode, but a standard Linux distribution running in a cloud, you really want pseudo access, and you can give someone that without wrecking your system security if they're in a nice virtualization layer. Another example is something like Samsung Knox running on a phone, where you get a VM in your phone for the employee to lock down and manage remotely next to normal Android on the same device. Now, some of the other challenges that there are subtle issues around monitoring when you've got virtualization going on. Again, there's a visibility problem, as with most isolation features. If you're going to check all the access control lists on your server to see who has access to what, then what about the access control lists inside containers or virtualized systems? You're going to have to check those as well, and you can't be thoughtless about this, otherwise you'll miss things. There's trouble at the interface. It's this nice idea that you can isolate everything away in its own separate VM, but you still need to share information between VMs, and so you'll still get information leakage via those and potential API-based attacks. And you'll end up having both usability and security issues because people will move to ad hoc mechanisms like using USB devices to get between the different VMs. An example of where this gets tricky and yet where this is useful is Bromium, who are a corporate provider of security mechanisms where you get a different VM per app. So Outlook runs its own VM, as does Microsoft Word, and so the idea is that a compromise of one shouldn't leak everything else in the other. So it doesn't matter if the program is buggy and riddled with memory safety issues, for example. But this is messy at the interface because the untrusted files that you're running, if you want to communicate between the VMs, have to go to the host and that is running all of them. And you often need to actually make this work where you can really have separate VMs for all of these programs that are used to communicating with each other in an operating system. You need lots of specific exceptions and plugins to make that work, like Outlook isn't allowed to render files itself in this setup. You have to prevent that by a plugin so that when you open it up, it really does only open up in the separate Word VM. So now we're on to containers, which is the hot new thing in the space where, hey, why would you want to pay all that cost for a VM? They're really space intensive. They've got that nasty page table walk. So why not just only isolate off the bits that you want? That's something that you'll get with Docker, for example. So you share your kernel between all of these different containers, but you isolate your application code and libraries from the rest of the system. All of the libraries that you want to access aren't shared from the kernel. They're within the Docker package. And that's actually very good for deployability. It means that you will run using known libraries rather than whatever's on the system. You won't have incompatibilities or missing dependencies. So it's great for deployability, but that's not necessarily a security thing. One thing that is a security thing is that, like with tools like NSJail, you can trap processes inside a jail. What that means is that you restrict syscalls by using tools like seccomp to choose which ones are allowed and which ones will fail. You change the root to a local directory and don't allow access outside of that. So that's one way that you can provide at least some isolation from the rest of the system. And you will virtualize within a container some things but not others. Process IDs, inter-process communication and namespaces will all be localized to the container and not visible outside of it. But you won't go as far as using that elaborate two-dimensional virtualized page table translation because you will be fundamentally using just the one kernel, unlike in a truly virtualized system. So really, it's a combination of syscall filtering and sandboxing to keep things in a region and to make communications outside of that region to more critical components filtered, logged, and reduce, therefore, the attack vector out of the container. Still, containers being a modern technology that hasn't really been tested that much, inevitably it promises a lot more than it can achieve a lot of the time. It's not the same as a VM. It's not meant for data isolation, really, even though it can do that to an extent. The trusted code base is still enormous. You've still got that whole shared kernel there, of which there will definitely be some bugs in it, because it's an enormous blob of C++ or C. Really, it's more about deployability, not security. And that means there are many subtle and not so subtle bugs in many existing deployments. Things like, even if your container really didn't have any bugs in the software, nearly 20% of the 1,000 most popular Docker containers have no root password. It's a blank root password. So they're not really isolated from each other, in that you can log into each of them without even guessing a password because there's just no security set. So you might think you're getting this really isolated system, but you absolutely aren't. Don't fall for the Titanic effect. Just because it's elaborate and fancy doesn't mean there won't be something dumb that goes wrong. But on the flip side, the deployability that containers give you, the package up once and run everywhere, might be a security feature. And why is that? Well, it's because it means if you discover a bug in a container, you can ship a fix to it very rapidly by just redeploying a new container. Usually the way most companies use containers, again this is from the Google SRS book, is that they're effectively read-only. You don't change them in production, you just issue a new container. So that rapid updatability whenever you change anything is enshrined in the development cycle, so that if you do ever have any problems, like known 0 days being rapidly exploited and therefore you need to patch rapidly, you've got a system that you already patch rapidly all of the time. So that does help in that scenario. And here we have a quote from the Google book, which is that the way Google compartmentalizes its services, the way that Google compartmentalizes the services, the microservices it provides, it runs everything in its own isolated little package where it can to reduce the vector of attack and to reduce cross-service attacks, is by role, location, and time. When an attacker tries to compromise a compartmentalized system, the potential scope of any single attack is greatly reduced. If the system is compromised, the incident management teams have options to disable only parts of it, to purge the effects of the compromise while leaving other parts operational. So if you have a microservice-based architecture, that means that you run jobs that don't need access to the same things as different accounts. It means splitting services across multiple different data centers, as long as you've got the cryptography there. That means if you're traveling over channels between data centers, that won't cause an information leak in and of itself, but that's something that you really should have in place since the Snowden leaks. And that gives you resilience as well by having it in multiple data centers. It limits the potential for DDoS, or at least certainly makes it harder. And rotating keys over time to limit scope and force the attacker to maintain presence. If someone gets in once and steals all of your keys, that isn't going to be enough as long as you've got key rotation in place that limits the extent to how long those capability keys are used for in each service. Right, so that's isolation, and there are various different ways of doing it that we've talked about, and each of them has a cost and a benefit in terms of the amount of security it provides, from just process level isolation to containers to virtualization to whole separate systems. And you can buy as any of them that you like in the cloud depending on how much defense that you need. But the other issue in cloud operating system security is trust. How do you know that what is running in the cloud is really what you want, and how do you know you're getting the promises around security that you're paying good money for? Well, this is all about TPMs and enclaves, so trusted platform modules, where, again, trust in this sense is not a warm, fuzzy feeling, and it's not trust necessarily as in something that's allowed to break your security policy. Here, it's trust as in you have this device in the system that you, the device operator, don't have ultimate control over. So in some sense, it's a treacherous computing, right? But if you're a cloud customer and you want to use cloud operator services, you want to be able to use those systems without having total trust in that cloud operator. Granted, you still have to have trust in the hardware vendor and the person who's actually built the trusted platform module in the first place, but that's another problem entirely. So there's this principle called remote attestation, where the idea is that you've got this TPM, which is your man on the inside, over in this untrusted system, potentially in the cloud, and what you want is that trusted platform module to send something that proves that your code is really being executed over there in the way that you intended it to. So the idea is that your trusted platform module takes a hash of the entire system and its state, sends that to you. You trust the trusted platform module. This contains cryptographic information that proves that it came from that trusted platform module, and it measures the system and says what's happening. And why would you need that? Why can't you just take it for granted that, well, your program's running over there and it's returning a result, so it must be that original program? Well, a lot of this is most easily exemplified by things like digital rights management, where let's say you've got your program not running in the cloud, but running on someone else's mobile phones. You're a content provider. And your program that deals with the DRM for this goes, if you're registered to watch the video, then play the video. Well, what if a clever person goes in and uses a binary editor and manages to edit out that line from the binary and runs this program instead with that line that disappeared? Well, it's not your program anymore, is it? And a lot of the time, the way that you get around this is just through obfuscation. You make it very hard to actually change the program in any meaningful way without breaking it completely, by adding in lots of misdirection to make it very difficult to understand and debug. But understandably, these things aren't very strong. They're very brittle. They can be broken by de-optimizers, so it's very much a cat and mouse game. Whereas the idea of a TPM is that it gives you proper guarantees. It gives you proper guarantees about what is running, even remotely, and means that you can stop the program from running, not respond to the system if it isn't doing what you want it to. And the way you do that is using a trusted platform module, which is this thing here. It's a very simple device that is basically a cheap microcontroller that's designed to be tamper-proof and sit on your motherboard rather than inside your chip. And all it has in there is a little bit of memory, a persistent key store that's non-volatile, so it doesn't zero when you turn it off, some simple cryptography hardware for, say, hardware AES or public key crypto, and an I/O bus over on the left to communicate with the outside world. And the way you use that is via a chain of verification. This simple hardware, which only has a very limited amount of storage, will store components off chip in memory, but it will all be protected by keys that will be inside the TPM. And if you want more keys, then you use that key inside the TPM to derive more keys based on things that are stored in the hard drive but are otherwise undecryptable without the TPM. And what you do is you use this for a secure boot process, like the thing that we've got on screen. So you start off with your TPM over on the left, and what that does is that the firmware is loaded and tested against the known key of the firmware, i.e. you attest that's what it is. If it matches, then the firmware loads the bootloader, measures the bootloader, sends a message to the TPM to store that and evaluate it. Then we pass, if it's correct according to TPM, we can then pass to the bootloader, which is then loads and measures the OS, sends a message to the TPM to make sure it matches, then pass execution on to the OS kernel, finally, which is measured and seen if it's correct. So you get this chain of verification between all of these parts where each gets progressively larger and is vetted by the last one and backed up cryptographically by the TPM. So the TPM measures if each of these things is secure or not, and assuming it gives it the A-OK, it can then measure if the next thing in the chain is correct. So we effectively take our firmware measurement, XOR it into the memory, take our bootloader measurement, assuming the firmware one was correct, XOR that in, take our kernel measurement, XOR that in to our memory, and then XOR in the software running above that. So you get this log that's stored in memory and cryptographically signed by the TPM that stores this chain, and the idea is that that's verified by things that are stored inside the memory, and so you can rederive it. Now, one of the big problems of this idea of trusted boot is that, yes, you can measure that the software that's running is the correct software, it's the right firmware you wanted, it's the right bootloader, it's the right kernel, it's not been altered in any way by any sort of malware or even deliberate tampering on part of the device owner, because you don't trust them either. But it doesn't say that it's not got any bugs in it, and your kernel in particular is going to be enormous. You're not going to be able to formally verify it, it's going to have bugs. Another issue is that these things are just really damn complicated. What happens if your bootloader changes slightly or your kernel gets some new updates? You get into an issue where there are so many different configurations that it's very difficult to know what the right one is and give a yes or no answer. So you end up having to go to measured boot instead, which rather than giving a yes or no answer locally on the machine, you send the attestation to a remote machine to log it and vet it in a more complex way. Again, much like the distinction between alarms and blockers in firewalls or physical security that we've talked about before. And we might be able to verify that it genuinely is your software running on the kernel you expect, running on the bootloader you expect, and the firmware that you expect. But when you've got lots of other untrusted actors, that really isn't enough, given that you've got this really massive trusted code base here. Just because you know it's the right thing doesn't mean that you know that it's correct, which it won't be if you've got this giant code base in low-level languages. There will be bugs in it. So let's say the rest of your system causes a buffer overflow in the kernel, fundamentally changes its behavior. It's not trustworthy anymore, even though it's the correct software. And therefore, everything that your software is based on, all of this big trusted code base, isn't trustworthy either. And so your software isn't trustworthy anymore either. Just even though it's the same software, it's not what you intended. So the proof isn't worth its salt in the face of those sorts of bugs. So a more modern alternative to the idea of this distinct TPM that measures and stores crypto secrets, which measures your CPU and the things running on it, is this idea of enclaves, like Trustzone, SGX, and SEV, which were briefly mentioned in the hardware security lecture. And the distinction here is that you don't need to measure or approve of everything on the system, because now you have this distinct world of the enclave, where you can run your private code and private data and limit the access to the outside world. And you can even run with untrusted code executing at the same time. You don't need to trust the entire operating system because you can limit the communication you have to it. In a sense, this is like hardware sandboxing. So what you do is you isolate off the attestation to just this small part here by making everything else, the rest of the system, irrelevant. And it also attests via cryptography that you're actually in an enclave, because that's something that you'll want to try and reduce the amount of snooping that can happen even by the operating system kernel on the code that you're running, because even the OS kernel may not be trusted in this scenario, especially even if you know what it is, because it still might have been tampered with by a bug. modulo attacks like on AMD's SEV from our second hardware security lecture, where in that case this proof wasn't actually proven at all because there was a bug in the way it was implemented. So always be wary of what you're really getting. So enclaves isolate you from the OS and give you precise attestation of just your software, but there's tension around access versus isolation. You still may want to access things from outside there to get anything done. If you're dealing with how Qualcomm implement this with their version of ARM's Trustzone, they let a trusted app map in regions of the host OS, so you aren't really that isolated if you don't want to be. Again, you don't want to be suffering from the Titanic effect, and when you're in an enclave, that limits the other security features that you get. Often they just aren't implemented very well or are too awkward to get running in the enclave. So you often get very weak address space layout randomization because you don't actually have that much addressable memory to begin with. So there's not a lot of randomization you can do. You often get very large trusted code bases around the edges that you still have to work with and have to assume are correct even inside your enclave. You still get information leakage, especially over debug channels out of the enclave on what the enclave is doing. Now those are arguably bugs, but there's nothing in most enclave specs that prevents side channels. Side channels are not a property that's enforced by the enclave, so even though you can't directly see what the enclave is computing on or the results of it, unless it deliberately chooses to write outside its result from the enclave, what you can see are the things it's accessed in the cache by the side channel attacks we've seen in the last lecture. And if you're vulnerable to that, that's meant to be your job. Intel just don't guarantee it, and neither does anybody else. There's often none of the features that we've come to rely on, like data execution prevention that forces you to use ROP attacks. So these traditional features often get left by the wayside, and that means that a lot of your lines of defense disappear even though you're inside the enclave. And while attestation is one of the few things that works pretty well in enclaves, many of the other features it gives you, it doesn't really give you. It's not that amazing for secrecy because of these side channel bugs. Attestation really does tell you what's running inside the enclave, but the integrity of the enclave can still be broken by things like the attacks on integrity that we saw in the second hardware security lecture, that e.g. by fault attacks can cause you to break what's happening inside the enclave. And if you'd be vulnerable to that sort of thing, and it's a realistic threat model, you need to be careful on what the latest attacks really are and whether there are solutions for them if you want to be guaranteed the properties of isolation and secrecy and attestation that you might want from an enclave. Okay, so that's an introduction to many of the relevant things that occur in security when you're in the cloud environment, where it's about isolation from other tenants, and it's about guarantees of what you're really running, and guarantees of who can leak what from your execution in an environment that you don't trust. For more reading, we've got several different chapters in security engineering. 7 is on distributed systems, so that's very relevant to this lecture, even though it wasn't for last lecture. 6 and 9 are on access control, but they're still relevant here. 27, which is on secure systems development, and 24 on copyright and DRM, which matters for attacks around the code that you're really running. That puts remote attestation in a slightly different context, where the solution, because of the lock-in challenges around enclaves, hasn't been to use them, it's been obfuscation instead up to this point. Here we have a paper on some of the problems that you get with Docker containers and why the security you think you might be getting might not be there in practice if you assume too much of the weaker elements, the dumber elements in your system. There are 2 chapters here from Google on how they use containerization and isolation in their systems. And then we finally got 2 papers here on how remote attestation works from a theoretical and practical level. Okay, see you all next time.